Hello everyone. In this lecture, we will learn the derivation of heat equation. Now consider this bar of length L placed horizontally on the x-axis. So assume this one end is at x equal to 0, another end is at x equal to L. Clear? We suppose that the cross sections of this bar, this one, are uniform, it means same, and that the lateral sides, lateral means outsides of the bar are well insulated so that heat inside the bar flows only in the x direction. It means you can assume that the outside area of this is coated with such a material that heat cannot enter from outside. So heat will flow from this side to this side. It means only in the positive direction of x-axis. Clear? Now just go through these notations. As uxt is the temperature at x at any time t. So basically u is a function of x and t. Similarly, E is a function of xt defined as a thermal energy density. Density means the heat energy per unit volume. This is important, per unit volume. Phi xt heat flux, amount of heat energy flowing in the positive direction across a unit surface, and per unit surface. This is the heat energy flowing in the positive direction per unit surface. Clear? Sx specific heat. Heat energy required to raise the temperature of 1 unit mass by 1 unit temperature. Clear? It means if you want to raise the temperature of a particular mass, particular unit mass by 1 degree, so this is the amount of heat energy which is required for this purpose. Clear? Rho x is the mass density, that is mass per unit volume. Clear? Now consider this slice of length delta x, and suppose the area of this portion is A, so area of this portion will be A because all these are uniform. So for this slice, the volume of this slice will be A into delta x. Clear? This is the volume. So thermal energy will be ext into A into delta x. Why it is? Because ext is the thermal energy density, heat energy per unit volume. If volume is A into delta x, then the thermal energy will be ext into A into delta x, because this is the volume. So this is the one way to find thermal energy. Clear? Now we will calculate thermal energy in another way. So thermal energy is also defined as the energy it takes to raise the temperature of the slice from a reference temperature, say 0 degree, to the current temperature uxt. Clear? So thermal energy, look at the Sx is the specific heat. Specific heat means the heat energy required to raise the temperature of 1 unit mass by 1 unit temperature. Clear? So look at this, rho x into A into delta x. Look at this and this one. Rho x is the mass density, A into delta x the volume. So this is mass density, means mass per unit volume. So if you multiply it by volume, this will give you the mass. Clear? And uxt is the temperature. So if you want to raise the temperature of this mass rho x into A into delta x by this temperature uxt, so the amount of thermal energy will be Sx into this rho x into uxt. So this will give you the thermal energy of the slice. Clear? Because equation 1 and equation 2 both represent the same thermal energy, that's why you can equate, you can compare these two, putting this value of thermal energy from equation 1 and equation 2 equal, you will get this equation, and simplify it, A into delta x will cancel out, so ext equal to Sx rho x uxt. Clear? So now you have the value of ext. Okay, just leave it. Now do some another calculations. Clear? Now according to the law of conservation of heat energy, the rate of change of heat energy is due to the heat energy flowing across the boundaries and internal sources of the heat. Clear? Here we are using the internal sources also. Internal sources mean in some of the cases internal sources may be 0. For example, if it is solid, then heat cannot produce internally. And in cases where suppose this bar is made up of different, you can say different layers. So, and suppose each layer is free to rotate in any direction, then in that case internal energy may be generated. Take otherwise, if no such cases are there, we can take internal sources, the heat energy generated by internal sources equal to 0. So this is a generalized case. Now for the slice delta x, on applying the law of conservation of heat energy. Clear? The rate of change of heat energy, this is, look at the rate of change of heat energy, this ext A into delta x, this is the heat energy. In this volume. So rate of change of this energy is given by del by del t, this ext into a to delta x. This is given by phi xt. What is phi xt? Look at this. Phi xt is heat energy flowing in the positive direction across a unit surface. So if the surface area is a, so phi xt, this is the heat energy at point x, and this is the heat energy at point x plus delta x. So this is the difference between these two. It means difference between. Clear? Phi xt a minus phi x plus delta x t a. So this is showing the difference between and difference of energy between these 2 points. Plus qxt. This is the energy generated by some internal source. Clear? And this delta x a, this is the volume. So this will give you the total internal energy generated by this volume. Clear? So look at this. If you divide it by delta x, clear, and a, so left hand side will be del by del t ext, because a and delta x are constant for this. So a will cancel out from each of the place. So this will become phi xt minus phi x plus delta xt by delta x, and this is qxt. Clear? Now from the Fourier's law of heat conduction, phi xt is the phi xt. Look at it again. Heat energy flowing in the positive direction, right, across a unit surface. So this phi xt is proportional to the change in temperature with respect to the distance. Why it is? Look at this h, and the sign of this is minus. So because the change in this heat energy depends in the change of the, look at this del u by del x. What is this? This is the change in u with respect to x. It means whenever this distance will increase, the heat energy will decrease. That's why we have written this minus. Clear? So this is phi xt equal to minus k0 is the constant which is known as thermal conductivity. Clear? So this is phi xt equal to minus k0 del u by del x. Now from equation 4, put the value of ext from equation 3 here, and this part, how can we write it? If you take minus sign outside, this will become phi x plus delta xt minus phi xt upon delta x. And if suppose delta x tends to 0 is a very small distance, so we can assume that limit delta x tends to 0. So this will become the derivative of phi xt with respect to x. So left hand side, this is the value of ext here, del by del t sx rho x uxt, and this is the derivative of phi xt. This part is when delta x tends to 0, this part is derivative of phi xt plus qxt. Clear? So sx rho x, these are constant. So further you can write, put the value of phi xt from here, phi xt minus k0 del u by del x. Clear? So this is k0 del square u by del x square uxt. You can do the calculation. This minus sign will be cancelled out because it is minus. So this is del square by del x square uxt. Whenever I am writing u here, this is u. This is basically a function of x and t. Clear? So this is del square by del x square uxt plus qxt. So finally del by del t uxt equal to k0 divided by this and 1 by sx rho uxt. Clear? And suppose you can assume this is a constant, you can assume this is equal to c square. If you assume that there is no internal heat resources, as I told you, so qxt, this part will be 0. Clear? It means it is a solid rod. So this equation becomes del by del t uxt equal to c square del square by del x square uxt. Clear? In short, how can we write? Del u by del t equal to c square del square u by del x square, where x is between 0 and n and t is greater than 0. Clear? So this equation represents the temperature at any point, at any distance x and at any time t. Clear? So this equation is known as one dimensional heat equation. Clear? Now look at this. How can we apply some conditions on that? The initial condition, when ux equal to 0 means when time equal to 0. So this may be a function of x, so we can write it, this is a function of x. Clear? X is between 0 and L. And boundary conditions, Now look at this. How can we apply some initial and boundary condition on this equation? Initial condition means when time t equal to 0, and suppose this ux 0 is a function of x at t equal to 0. So this is a function of x equal to x is between 0 and l. Now boundary condition, two boundary conditions will be there. One when x equal to 0, and suppose at that point temperature is T1, and when x equal to L, suppose this temperature is T2. Clear? So T is greater than 0. So these are initial and boundary conditions for this one-dimensional heat equation. So this is the derivation of one-dimensional heat equation. I hope that you got the concept, and now you can derive the one-dimensional heat equation. Thank you.